Welcome to this rigorous lecture on using artificial intelligence for deep research. Today we'll explore the fundamental principles, methodologies, and practical applications of AI-assisted research workflows. First, let me define what we mean by deep research. Deep research is the systematic investigation of a topic that goes beyond surface-level information to uncover fundamental principles, causal relationships, and novel insights. Deep research involves synthesizing information across multiple layers of abstraction. You start with raw data, build intermediate representations, and ultimately construct high-level theoretical frameworks. It requires rigorous critical evaluation of sources, methodologies, and the validity of conclusions. You must constantly ask, is this evidence reliable? Are there confounding factors? What are the limitations? Let me show you the hierarchy of research information. This is crucial for understanding how AI can assist at different levels. At the bottom we have raw data and primary sources. Moving up, we process this into analyzed information. Then we synthesize knowledge from multiple sources. Finally, at the top, we generate novel insights and theoretical frameworks. AI assists research through three fundamental pillars. Let me explain each one in detail. The first pillar is information retrieval and filtering. Modern research involves navigating vast information spaces. A typical academic field produces thousands of papers annually. Scientific literature doubles approximately every 20 years. If we call time t in years, the volume of information grows as 2 to the power of t divided by 20. Here's a critical question. How do we efficiently find relevant information in this exponentially growing space? Traditional keyword searches are insufficient. The answer is that AI systems use semantic understanding through embedding spaces. Instead of matching exact keywords, they understand conceptual similarity. The second pillar is pattern recognition across multiple sources. Humans are limited in the number of sources they can simultaneously analyze. Psychological research shows human working memory holds approximately 7 plus or minus 2 items. This is Miller's law from cognitive psychology. AI systems can simultaneously analyze thousands of documents and identify recurring patterns, contradictions, and consensus views that would be impossible for humans to detect. The third pillar is hypothesis generation and testing frameworks. I can suggest novel hypotheses by identifying gaps in existing research. Now let me present a practical 5-stage pipeline for using AI in deep research. This framework is based on established research methodologies. Stage 1 is problem formulation and scoping. You must precisely define your research question. A well-defined question is specific, measurable, and has clear boundaries. Compare a broad question like, how does climate change affect ecosystems, versus a refined question that specifies the quantitative relationship, the specific variables, the ecosystem type, and the time period. Use AI to explore the space of possible questions. Ask the AI, what aspects of this topic are well studied? What are the open questions? What methodologies have been used? Stage 2 is comprehensive literature mapping. This is where AI truly excels compared to traditional methods. A traditional literature review might involve linearly reading 50 to 100 papers over several weeks. This is time-intensive and prone to selection bias. An AI-assisted approach can hierarchically cluster thousands of papers, identifying major research threads, methodological families, and conceptual relationships. Let's do a back-of-the-envelope calculation. If n is the number of papers, t sub read is time per paper, and alpha is the fraction you still need to read carefully, the time saved is n times t read times 1 minus alpha. For 1,000 papers at 2 hours each, if AI helps you skip 95% of irrelevant papers, you save 1,900 hours. That's nearly a full year of work at 40 hours per week. Stage 3 is critical synthesis and cross-validation. This is where human expertise remains essential. Here's an important question. Can we trust AI-generated summaries completely? What are the potential failure modes? The answer is no. AI systems can hallucinate facts, miss subtle nuances, and misinterpret specialized terminology. You must always verify critical claims against primary sources. The optimal workflow is iterative. Use AI summaries for quick overviews and hypothesis generation, then verify critical claims with primary sources. Go back and forth between these modes. I recommend the cross-validation triangle method. For any critical claim, verify it through at least 3 independent sources using different methodologies. Stage 4 involves quantitative analysis and modeling. A. I can help identify appropriate statistical methods and check calculations. Consider a meta-analysis of effect sizes from multiple studies. You need to account for sample sizes, study quality, and publication bias. The pooled effect size theta equals the sum of weighted individual effect sizes divided by the sum of weights, where each weight, W sub I, typically depends on sample size and variance. Each weight, W sub I, equals 1 divided by the sum of within study variance sigma sub I squared plus between study variance tau squared. A. I can automatically extract reported statistics from papers, check for calculation errors, and flag potential p-hacking or selective reporting. Let's do another calculation for publication bias detection. If we have 30 published studies, how many unpublished null results might exist? The file drawer number estimates unpublished studies. It's approximately 0.05 times the number of significant studies divided by alpha minus the number of significant studies. For 30 significant studies at alpha equals 0.05, we get 0. But if these studies are barely significant, with alpha near 0.1, we might have many more unpublished studies. Stage 5 is insight generation and framework building. This is where creativity meets rigor. Use AI to generate multiple competing explanatory frameworks for your findings. Don't accept the first explanation. Generate at least 5 alternative hypotheses. From your core finding, branch out to multiple hypotheses. Then systematically evaluate each one against the available evidence. Rank them by explanatory power and parsimony. Let me present a concrete case study from drug discovery research. This illustrates the power of AI-assisted deep research. The problem was to identify novel compounds for treating a rare metabolic disease affecting only 10,000 patients worldwide. Traditional drug discovery takes 5 to 10 years and costs approximately $2 billion. Much of this time is spent on literature review and initial screening. Using AI-assisted research, one team went from problem formulation to clinical trials in 18 months. How did they achieve this acceleration? Step 1. AI systems mapped the entire protein interaction network for the disease pathway, analyzing over 50,000 papers in molecular biology. Step 2. From this network analysis, they identified 200 potential drug targets that traditional methods had missed. Step 3. They performed virtual screening of over 1 billion chemical compounds against these targets using machine learning models trained on existing drug data. They tested 1 billion compounds virtually but only 10,000 physically in the lab. This ratio of 100,000 to 1 shows the screening efficiency. Assuming $1 per virtual test versus $1,000 per physical test, the cost reduction factor is approximately 1/10 compared to purely physical screening. What were the critical success factors in this case study? Let me identify 5 key elements. First, they had a crystal clear problem definition with measurable outcomes. Not just find a drug, but find compounds that modulate specific pathway proteins. Second, they used a hybrid workflow where AI suggestions were validated by human experts at multiple checkpoints. No blind acceptance of AI outputs. Third, they integrated multiple data modalities: genomic data, protein structures, clinical observations, and chemical properties. AI excels at multimodal integration. Fourth, they used iterative refinement. Initial AI predictions were tested experimentally, and results fed back to improve the models. This closed-loop approach is essential. Fifth, domain experts were involved at every stage. The AI augmented their capabilities but didn't replace their judgment. Now let me discuss common pitfalls in AI-assisted research and how to avoid them. These are based on systematic analysis of failed research projects. Pitfall 1 is over-reliance on AI without verification. Some researchers treat AI outputs as ground truth. This is dangerous. The solution is to always verify critical claims by examining primary sources. Use the 80-20 rule. AI for 80% of initial screening, human verification for the critical 20%. Pitfall 2 is ignoring AI limitations and biases. AI models are trained on existing literature, which may contain systematic biases. Training data biases, like publication bias, geographic bias, and language bias, get amplified in AI model outputs. The models may give overconfident predictions and miss important edge cases. The solution is to actively search for counter-evidence. Don't just ask what supports my hypothesis. Ask what contradicts it, what alternative explanations exist. Pitfall 3 is neglecting methodological rigor in favor of speed. AI makes research faster, but speed without rigor produces garbage. Maintain systematic protocols. Document every decision point. Why did you choose this search strategy? What were your inclusion and exclusion criteria? What assumptions did you make? Let me introduce some advanced techniques. First is semantic search using embedding spaces. Traditional keyword search has low recall. You might search for neuroplasticity, but miss papers using terms like synaptic remodeling or neuronal adaptation. Semantic embeddings map concepts into high-dimensional vector spaces, where conceptually similar ideas are close together even if they use different words. Similarity between concepts A and B is computed as the cosine similarity, the dot product of their embedding vectors divided by the product of their magnitudes. In practice, if the similarity score exceeds 0.8, the concepts are likely related even if they use completely different terminology. Another advanced technique is citation network analysis. This reveals the structure of scientific knowledge. Each circle is a paper. Lines represent citations. The red circle is a seminal paper with many citations. Analyzing this network reveals influential ideas, research communities, and knowledge flow. Paper influence can be quantified as the sum over citations I of each citation count divided by the time since publication T minus T sub I plus 1. This accounts for both volume and longevity of impact. The third advanced technique is automated hypothesis testing frameworks. A. I can generate testable predictions from theory. For example, if theory X is true, then variable Y should correlate with variable Z in specific populations. A. I can automatically search datasets to test this prediction. AI systems can scan thousands of public datasets, identify those containing variables Y and Z, perform appropriate statistical tests, and report the results. If the p-value is less than alpha, typically 0.05, we have statistical support for the theory's prediction. But remember, correlation doesn't prove causation. An important question: what about reproducibility? If we use AI tools, can others reproduce our research? The answer is yes if you document everything. Record which AI tools you used, what versions, what prompts, what settings. Treat AI tools like any other research instrument. That must be documented. Let me quantify the research acceleration from AI assistance. These numbers come from systematic studies. The speedup factor equals traditional research time, divided by AI-assisted research time for equivalent depth and quality. For literature reviews, typical speedup is 3 to 10 times. A review that took 3 months might now take 2 to 4 weeks. For data analysis, speedup is 2 to 5 times. AI can automate routine statistical tests and visualization, but human interpretation is still required. For hypothesis generation, speedup can be 5 to 20 times. I can rapidly generate many candidate hypotheses from existing theory. Overall, the complete research cycle from question formulation to publication might see 2 to 4 times acceleration. But quality must not be sacrificed for speed. Now let me address crucial ethical considerations. AI-assisted research raises important ethical questions. Issue 1 is attribution and intellectual contribution. If AI helps generate insights, how do we attribute credit? Is AI a co-author? Current consensus is that AI is a tool, not an author. Just as we don't list statistical software as authors, we don't list AI as authors. But we must disclose how AI was used. Issue 2 is bias amplification. If AI is trained on biased literature, it may amplify existing biases and research conclusions. Mitigation strategy. Actively seek diverse sources and perspectives. Don't rely solely on English language papers. Include research from different geographic regions and methodological traditions. Issue 3 is access inequality. Advanced AI tools may be expensive, creating a divide between well-funded and underfunded researchers. Solution: support development and use of open-source AI research tools. Democratizing access ensures equitable research advancement. Let me provide a practical roadmap for implementing AI in your research workflow. This is a step-by-step guide. Month 1. Spend time learning the basics of AI tools. Understand their capabilities and limitations. Practice on non-critical tasks. Month 2. Apply AI to literature review for an existing project where you already know the field. This allows you to evaluate AI accuracy. Month 3. Develop your verification protocols. What checks will you perform? How will you validate AI-generated information? Month 4. Integrate AI into your full research pipeline. Start with a new project, where you can design the workflow from the beginning. Months 5 and 6. Refine your approach and document best practices. What works well? What are the failure modes? Share your findings with colleagues. An important question is, how to measure research quality when using AI? Speed without quality is worthless. Metric 1. Citation to source ratio. High-quality research cites primary sources, not just summaries. Aim for at least 50% primary source citations. Quality ratio equals number of primary sources divided by total citations, should be at least 0.5. Metric 2. Claim verification rate. What fraction of AI-generated claims did you personally verify? Aim for 100% of critical claims. Metric 3. Alternative hypothesis consideration. Did you explore multiple explanations? Quality research considers at least 3 alternative frameworks. Let me conclude with future directions in AI-assisted research. The field is rapidly evolving. Trend 1 is multimodal AI that integrates text, images, data, and code. Future systems will seamlessly work across all these modalities. Trend 2 is real-time collaborative AI that works alongside researchers, suggesting experiments, flagging inconsistencies, and updating analyses as new data arrives. Trend 3 is automated reproducibility checking, AI systems that can read a methods section and automatically attempt to reproduce the analysis. Trend 4 is cross-domain knowledge synthesis, AI that identifies relevant insights from completely different fields and suggests novel connections. Let me emphasize the nature of the human-AI partnership in research. This is not about replacement, it's about augmentation. Humans bring creativity, intuition, ethical judgment, contextual understanding, and nuanced interpretation. AI brings scale, speed, pattern recognition across vast datasets, consistency, and perfect memory. Together, they create synergy. Humans ask the important questions. What should we study? Why does it matter? What are the implications? If AI helps explore the solution space efficiently, it can rapidly test many approaches and identify promising directions. Humans interpret results in the broader scientific, social, and ethical context. What do these findings really mean? What should we do about them? Let me summarize the key takeaways from this lecture. First, AI can dramatically accelerate research workflows, but it doesn't replace the need for methodological rigor and critical thinking. Second, use AI for breadth of coverage, pattern detection, and initial screening. Use human expertise for depth, validation, and interpretation. Third, always verify critical claims by consulting primary sources. Never blindly trust AI-generated summaries for important conclusions. Fourth, document how you used AI tools just as you would document any other research method. This ensures reproducibility and transparency. Fifth, maintain high ethical standards. Be aware of potential biases in AI systems and actively work to avoid amplifying them. Sixth, develop systematic verification protocols. Don't just use AI casually. Have a structured approach with clear checkpoints. Seventh, focus on the research question, not the tool. AI is a means to an end. The goal is insight and understanding, not just using AI. Let me leave you with a final thought. The most powerful research comes from the synergy between human insight and AI capabilities. AI handles the mechanical aspects, searching, sorting, summarizing, calculating. This frees human researchers to focus on what we do best. Humans can focus on creativity, asking novel questions, interpreting results in context, and understanding what the findings mean for society. Together, human-AI partnerships can tackle research problems that were previously impossible due to scale, complexity, or required interdisciplinary synthesis. The future of research is not human or AI, it's human and AI working together. This collaborative intelligence will drive the next generation of scientific discovery.